Morning everybody. Welcome to this lecture on the capturing of CO2 and storing it underground. My name is Joe Cartwright and it's a pleasure to talk to you this morning. A little bit about myself. I've been at Oxford for about 10 years, previously in other universities, Imperial and Cardiff University, Cardiff born and bred. And most of my career, which spans about 40 years now, I've studied sedimentary basins and how they're filled and how they deform and how fluids are stored within them. Those fluids could be either petroleum or CO2 or groundwater or mineralizing fluids. So the study of fluids in sedimentary basins is pretty critical really to the exploration, discovery and exploitation of lots of resources that human society relies upon. Let me switch to the PowerPoint. So I'll be talking about how we might store CO2 that we need to capture from industrial processes, possibly even from the atmosphere itself, and store it safely in the subsurface. And this presentation is co-authored with one of my colleagues, Professor Michael Kendall, a geophysicist, and his research assistant Tom Kettlety. And we're working together on trying to sort of de-risk the process of inserting CO2 deep underground to remove it from its hazardous role in global warming. And the need for doing this is pretty evident here with this kind of future prediction of how we might reduce emissions sufficiently to meet the 2050 targets that are being set internationally. So this is a sort of a crystal ball model prediction. The axes are in years on the bottom, and on the left-hand side in gigatons of CO2 that we need to store or remove and mitigate by different means. And CCS is the orange, represents what, about 15% by 2050. So a pretty significant fraction. Renewables, you can see, very significant as well. But the greatest mitigation method, of course, is by greater energy efficiency, which accounts for some 40-odd%. So there's no single silver bullet that we can use to meet these targets of net zero by 2050. But you can see from this plot that CCS, carbon capture and storage, is a pretty significant individual contributor. Now, CO2 is produced by fossil fuel consumption, exploitation, cement manufacture, a host of other industries, chemicals, refining, pulp and paper, iron and steel, even bioenergy. The big player, of course, is coal-fired power generation, so electricity generation using coal-fired power stations. And although we'd like to remove that from the equation, clearly in the developing nations, which have huge coal resources, that's just a non-starter. So perhaps CCS can help mitigate the impact of that really significant generation of CO2 and by coal-fired power stations. And then if we look at the plot on the right, we'll see that what we have at the moment in the way of capacity to remove CO2 and store it underground is really tiny compared to what we need by the year 2050. Excuse the sounds in the background. I've got my elderly dog with me in my office and he's having a bad time of this hot weather at the moment. So you can see 2020 we have 40 million tons per annum, and what we need to be able to store in 2050 is over 100 times that, and that's graphically displayed there with the different sources of the CO2 and how we need to upscale our current CCS capacity by over 100-fold. which is going to require huge willpower on the behalf of governments, technological know-how, and obviously finance. It can be done, but we'd better not hang around too long, and we better crack on with this. And then just to flick back for that figure on the left, you can see the grey tones is the coal, and the various other contributors there sort of fairly uniformly distributed. Bioenergy is a surprisingly large fraction of that CO2 output. So yeah, some interesting individual contributions there to the CO2 that we need to extract. And of course, if we could somehow mitigate the cost of this by using that CO2, that would be better still. So there are a number of ways that we can take the CO2 that we capture at the industrial chimney or at the site of production of the CO2, air conditioning units, factories, pipelines, ships, and we need to then find a way of compressing it and moving it to the point of storage or moving it to the point of use. So it can be used, and plenty of research going on into how we can use that CO2 constructively and add value to the capturing of the CO2 from the original source. But I'm not going to be dwelling on that. That's for somebody else more qualified to talk about. My understanding of the subsurface allows me to think about these things, how we can store the CO2 into saline formations and depleted oil and gas fields. And I'll talk a little bit more about that. So just to set the scene, we have a kind of cross-section through the Earth here, rather cartoon-like cross-section of the Earth. And what you can see is a number of different options there, geological layers with different kinds of characteristics, with different kinds of geometry, and these boreholes that are drilled down there with derricks on the surface representing the position of the boreholes are telling you something about the different kinds of storage sites that exist in the subsurface for pumping very high pressure CO2 and removing it from the Earth system, hopefully keeping it down there long enough to make an impact. And those different sources are saline aquifers, depleted oil and gas reservoirs, oil fields where the oil is very viscous and you use CO2 to reduce the viscosity, and also methane in coal beds can be displaced by the injection of CO2. So the last two are, you're back into the vicious circle of using the CO2 to create more fossil fuel that you use at the surface to create more CO2. So I'm not particularly keen on that, although there's an economic prerogative that does come into play. But my interest is in actually removing the CO2, and many researchers like me are motivated in the same respect to try and use our knowledge of the subsurface to inject the CO2 into places where it's safe to store. It won't affect whatever we're doing at the surface, the ecosystems at the surface, and it will stay there for long enough to make an impact. So how is CO2 trapped in geological formations? Well, we need some kind of geometry, and this is the picture on the right. We need a geometry where there's a porous and permeable unit, a layer, like, for example, a sandstone or a limestone. These are rocks with intrinsic porosity, that space between the grains. Think of a beach sand, for example, and pouring, your can of Coke. It just disappears down into the beach sand. So that's porosity. And if you had beach sand with mud mixed in, that Coke, when you poured it onto the beach sand, would take longer to sink in. So that's permeability. So you need porosity and permeability such that when you drill a borehole into that layer and inject the CO2, it can flow into the formation and displace the water that exists there in the pore space. It's not a vacuum. There's water in the subsurface in pore space. And when that CO2 displaces it, it's then effectively stored. And it's stored and prevented from coming back up to the surface by impermeable or low permeability layers like clays. Clays are very good, but also salt, rock salt. And these are sealing formations that prevent a buoyant fluid rising back up to the surface. So these are the main geological prerogatives, therefore, to store CO2 safely underground. So CO2 is injected as what we think of as a supercritical fluid, and that means that a volume of 100 cc's at the surface is 0.27 cc's at the point of injection at a depth of a couple of kilometers. The critical depth is about 800 meters, where you achieve supercriticality of CO2. So you need to have an injection pressure equivalent to that, and then drill a borehole down a minimum of 800 meters or more, wherever that suitable formation is found, and inject the CO2 under high pressure into the formation. Sometimes the CO2 will be trapped just by capillary forces. These are interfacial forces between the mineral grains and the fluid. Sometimes it will be trapped by going into solution in the pore fluid, and sometimes it will be trapped by reacting with the minerals and forming a carbonate mineral, a calcium carbonate or a magnesium carbonate, and will be permanently fixed in the mineral structure. Residual trapping, solubility trapping, and mineral trapping all occur, but at different timescales than structural trapping. So what we're really primarily interested in is trapping this stuff underground in the immediate near future and not seeing any movement of it back to the surface on a timescale of perhaps 10,000 years. So how have we been doing this? Well, principally it's been done by the petroleum industry. So where does subsurface technology reside? In the petroleum industry. And poor little dog. And so that expertise and knowledge and ability to do the CO2 storage underground is actually sitting within the petroleum companies. And they will be absolutely instrumental in achieving the goals that we set them, and will need to be incentivized so to do. So various different companies have been trying this CCS for the last 20 to 30 years. This one in Canada has been going that sort of period of time. It's CO2 coming from a coal gasification plant, pumped via a pipeline, underground, and about 40 million tonnes has been stored. So that's only emissions from 500,000 cars per year. So it's a pilot, really. It represents a feasibility study. Another such feasibility study in Algeria worked for a few years, but then there were some technical problems with the drilling, and that was called to an unusually early halt. And that does emphasize that things can go wrong. This is a complicated engineering challenge. So this one was suspended, the operations were suspended because of geomechanical issues, and that's kind of code word for saying drilling problems. So the process of drilling and injecting is not without its difficulties and challenges. So the section on the bottom right there shows you the geological formations. The blue layer at 20 meters thickness at a depth of about 2 kilometers is the formation into which the CO2 was injected. And you can see the black lines coming from the surface are the trajectories of the boreholes. And then there are some boreholes which are drilled specifically for monitoring purposes, and that's called a microseismic array, and that would detect any earthquakes being generated by the drilling and injection operations. And as we'll see a bit later, that's one of the major risks. So where are these kinds of operations going on? Well, they're in China, Northwest Europe, North America and Australia principally, a little bit in Brazil and in Saudi, one in Iceland, interestingly, trying to inject CO2 into basaltic formations. So very much in its infancy, only a few long-running pilots. And the take-home messages from this sort of introductory section of the lecture are that we definitely know how to do this. The oil industry's been doing it successfully for 20 to 30 years, and there's an urgent need to scale up. And we need to diversify the industrial application of CCUS to incentivize and make the economics of this more palatable. This cannot happen without oil and gas industry involvement. In fact, it will need to be led by the oil and gas industry. And that's as well to remember when we're kind of putting the oil and gas companies up for, being pilloried in the kind of, the theatre of public opinion. We better remember that, we need to keep them on board if we're going to fix this problem from a CCS viewpoint. There's clearly a need for research and development, always, to make things safer, to make things more efficient. So a little bit more on the details of geological storage. There are two principal options. On the left, shallow saline aquifers. These are porous and permeable reservoir units that are in a trapped configuration that are under the overburden, which is generally much lower permeability. And we inject the CO2, as illustrated there, into the reservoir unit and watch the CO2 plume migrate through the reservoir, displace the water, gradually fill the reservoir, and hopefully not migrate upwards to the surface. So those are the conditions that we need to really evaluate, whether we've got enough storage space to inject a significant volume and whether that volume of CO2 will remain in the subsurface and be safely stored in the geological formation. The second option is to go to places which were explored for successfully, oil and gas, old oil and gas fields that are no longer used, where we've extracted a lot of the oil or gas from that particular trap. The trap, of course, has been proven by the fact that oil and gas have stored there over time, and then inject CO2 into that pre-existing well-defined trap. And that's a very plausible and appealing strategy, but we should bear in mind that injection of CO2 at a rate which is much greater than the rate of natural feeding of oil and gas into the trap might lead us into different physical conditions. It's like inflating a balloon very slowly with a very sort of weak membrane, the balloon itself, versus pumping it up really fast where you might expect it to burst. So the rate of injectivity might be a critical issue when it comes to the integrity of the sealing conditions for these old depleted gas or oil fields. So just a few, reminders about some of the basic principles involved here, in case you're unfamiliar with these kinds of terms and concepts. So most importantly, porosity. The amount of CO2 that we can inject depends critically on the parameter called porosity. It's the pore space. So what you can see there is a sort of a familiar pack of sand, and you can see grains on the left, and then the images on the right are sections taken through that, blown up and displayed in a particular way to show you what the grain distribution looks like. The grains of different sizes and shapes, different sphericity, roundness, angularity, and the way that they pack together. And the way they pack together clearly determines the porosity, the void space, which is shown in blue in the images on the right. And you've got a zoom of that black box to see a little bit more the details. So you can see that the porosity correlates with the grain size being the sort of mean diameter of individual grains. It also correlates to some extent with the shape of grains. So the ideal grain is a sort of a spherical grain in a packing arrangement that will give you perfect porosity distribution, uniform grain size and sphericity. Maximum theoretical porosity would be about 40%. And typically in the subsurface, sandstones are not perfectly packed and perfectly spherical grains with uniform grain size. And so real natural sandstones give you a porosity of sort of 10 to 30%. So you have to picture down at 1 kilometre, a sandstone has the potential to store about 10 to 30% of its rock volume. So whatever volume that rock occupies, only max of a third of that volume will be available for storage of CO2. And you need to know these numbers in order to calculate how much you can actually store, and how much you can store factors into the economics of the whole proposition. Now, how rapidly you can inject CO2 into that sandstone depends on the shapes and the sizes of all of those spaces between the grains. So the little nooks and crannies that excuse me, that are the boundaries between the grains, and that determines this parameter called permeability. So we've studied this a lot from the oil and gas point of view. Oil companies really have a huge knowledge of the relationship between porosity types, grain size distributions and permeability, and you need to be able to calculate that permeability or measure it directly in order to compute your injectivity rates. And that is the rate at which you can pump CO2 into the formation, and that is really a critical parameter for the economics. It's also a critical parameter for the safety of the injection. So the intrinsic permeability will be a crucial parameter to calibrate, to forewarn ourselves of when it comes to the safe injection of CO2 at rates that are economic and meet our needs. So how we can work out permeability is by understanding the internal structure of these reservoir formations, and for that we use X-ray tomography. We can use numerical modelling, a forward modelling approach, and we can run forward modelling simulations on fluid flow of different fluid properties and viscosities to calculate what are effective permeabilities. So that's a huge research challenge in its own right. Using all of our technological capabilities in X-ray tomography, coupled with our abilities in numerical modelling, is the role of reservoir engineering and reservoir geology combined to try to work out the parameter of permeability and how it varies on a scale of what you can see here, hundreds of microns, to a scale of kilometres. So let's look at some examples of depleted oil and gas fields that have been trialled. And here's one from South Australia. It's a geological cross-section that I'm showing you. And what you can see is a couple of boreholes. And the boreholes are drilled into a depleted oil and gas field. So there's lots of geological background knowledge here that was acquired over many years in order to develop this oil or gas field. It's got the advantage that it's close to existing pipeline infrastructure. There's huge amounts of data, and from the production of the oil and gas over a long period of time, we know quite a lot about the behaviour of this reservoir. On the negative, it's deep, it's structurally deformed. That means it's broken up by lots of faults. Those are the inclined black lines that you can see on the slide, which chop up the geological formation. It has higher intrinsic formation pressure, and it has lower porosity and permeability than we'd ideally like for example, that we might have in a shallower saline aquifer, because porosity and permeability generally reduce with increasing burial depth. So that has been running now for a number of years, and a lot of information has been acquired about the effectiveness of injecting CO2 into a depleted oil and gas field. And I should just finish looking at that slide by saying none of these things are perfect, none of these options, but it's a question of weighing the risks and the benefits of these different options. And having these pilots running for a number of years gives us greater insight into these risks. Well, geologists have been able to calculate the storage potential of depleted fields. We know where the depleted fields are. We can compute how much volume of CO2 could be stored in each one of those. And there are the numbers that has come from huge amount of computational effort by a number of agencies around the world. And you can see that the big player in this is the US. Huge volume of, this is millions of tons, so there's 200,000 million tons of CO2 could potentially be stored in depleted oil and gas fields in the US. And that nicely tallies with CO2 production. And the US is, I think, still the largest producer of CO2. China's very close, maybe has already overtaken it, but has much less in terms of storage capacity in oil and gas fields. So, you know, a country like the US could do an awful lot by injecting CO2 into known, depleted, tried and tested underground storage sites in these oil and gas fields. The UK, we're kind of a bit player in this. China, disappointingly low. So the big standout figure there is the US. The US also has phenomenal storage capacity in shallow saline aquifers. So these are rocks like sandstones and limestones that occur at depths of perhaps 1 to 2,000 meters. And the brownish colors there show you all the sedimentary basins in the United States, and the sedimentary basins that are more than 800 meters thick are potentially storage sites for CO2. And then the USGS has gone around and actually calculated, the US Geological Survey has calculated, you know, precise figures for which of these sedimentary basins could be storage sites. So, you know, the quantification of storage potential is very advanced in certain countries, and the US leads the way on that. We're nothing like as advanced in the UK, but we have a reasonable idea of where we could store in the UK. And these are some of the sites identified by the British Geological Survey, with capacities on land and offshore, principally in the North Sea, in shallow saline aquifers in the sort of reddish orange colour, and then in saline aquifers where there's a trap in the green colour, and then hydrocarbon fields in the sort of bluish circles, and that's principally in the southern North Sea. And the sources are those kind of filled greyish circles, so they're all on land. So the vast majority of storage sites identified by the BGS are in confined or trapped saline aquifers, with unconfined saline aquifers being a significant portion of the total storage capacity. Well, one of those saline aquifers, which has characteristics of unconfined and confined geometry, it has a geometry which varies from being quite open, sort of open-ended, to being sort of bumps and underground hills that provide perfect structural trapping opportunities, is the Sleipner region of the North Sea, where Equinor has been injecting CO2 for the last 30 million years or so at about 1 million tons per annum. And it's up in the site of a bunch of oil and gas fields, so there's a huge infrastructure, and these shallow saline aquifers at about 1,000 meters depth, and beneath there is a large gas field. So boreholes can be drilled quite efficiently into that region. And these boreholes, shown here in a sort of cutaway of the subsurface, the reservoir there being the Sleipner, the Utsira formation above the Sleipner field, and that's shown here in the borehole coming down from the platform at Sleipner and injecting CO2 in that sort of blue legend, with red layers being where the CO2 plume is injected into the formation. It has a huge storage capacity. Its positives are that it's geologically young and very simple. It's got very predictable behavior. It's shallow. The pressure regime is absolutely favorable to injecting huge volumes, and there aren't many faults. So what could go wrong? Well, that's a subject of research. We should always be thinking the unthinkable, that something could go wrong. But for 25, 30 years, nothing has really gone astray. That's not to say that that will remain true for the next hundreds of years. And that's the job of the forward modelling team, who have to try and anticipate risks, for example, with changing geological conditions like a new ice age. That's what we call a geological cross-section. 4 or 5 boreholes give us the constraint on the geological layering, thicknesses and the material properties that we've already established by drilling these boreholes. It's fairly simple layer cake geology. By that I mean the layers are kind of stacked one above another, younging upwards, and there's huge lateral extent. If you look at the scales there, that Utsira sand, which is the storage reservoir, extends over a huge area, and it has a wonderful seal just above it. So fabulous example of a shallow saline aquifer. The seismic data, which is a sort of a monitoring or imaging technique, it's a bit like sonar. We send seismic waves down into the earth and record their reflections from the geological layers, and we get an image that looks a bit like, an MRI scan of a human being, but we're seeing the geological layers rather than the layers of the internal organs, and the different colours there represent different physical properties of those layers. And this technique is absolutely critical to finding oil and gas, and is widely used now in searching for carbon capture and storage sites. It tells you a lot about the geology. When you combine it with drilling a borehole, you get a fabulous view of the subsurface, like having a geological Hubble telescope turned inwards. And it gives you the ability to actually see the CO2. So the seismic data in this particular instance, I don't know if you can see my cursor moving, I hope so. In the bottom right here, you can see different colours, and those colours represent changes to the seismic response that injecting the CO2 brings about. So absolutely amazing technique. It's very expensive though, so we'll need to deploy this to very good effect, I think. Anyway, you can acquire this seismic data repeatedly over a number of years and then create images like these. So these are the vertical seismic images on the bottom diagram, a time series. You've got the ages there showing the rather steady growth of the CO2 plume with that zone of increased colour density, reds and blues signifying the presence of CO2. And then if you were to imagine having that data in a computer and slicing it horizontally at the level of the reservoir, that's the image you see above. You can see the growth of the plume in the horizontal dimension in those little plots above. So those are the time series with the injection point indicated, and the colours show the gradual expansion of the zone of injection of the CO2 into the reservoir formation. And that's something we record as 4D seismic data, and tells you a great deal about the growth of the injected material. So I hope that's given you a flavour of how we go about doing this, what the storage options are. We can see that we can store, technologically, we're capable of storing in both saline aquifers and in depleted fields, and they have different risks and benefits. There's huge volume potential in areas close to sites of active production. So both of these options are absolutely economically viable at the right price, because it is costly to drill wells and inject and record seismic data and monitor for leakage. And we'll talk more about monitoring in the next segment. So, we can do this, but it's not cheap and it requires gearing up and huge investment. So Tom put together this final segment for us for this presentation on the risks and challenges, focusing more on what might go wrong and what we need to do to ensure things don't go wrong. So there may be problems associated with injectivity. It might not work as we like it to. We might not get as much in as we want at the right rates. We might trigger earthquakes. That's called induced seismicity. And we might see the CO2 leak back up into the overlying formations. And in order to mitigate those risks, we need to monitor, and we need to do it at the right scale to be safe, but at an economic kind of scale to make sure that we don't overprice the monitoring to the point where we're not able to feasibly store CCS underground, carbon dioxide underground. Complicated slide this, lots of things going on. That diagram shows the sort of schematic of injecting CO2 from the borehole and the plume rising and the volume of the trap. And those little graphs are the injection pressure and the pressure of the CO2 at the point of the borehole. And then the pressure in the reservoir over a period of time. So you can see that there are different scenarios there where you build up the pressure and then it drops off, or where you have an exponential decay in the pressure as you go further from the well. So two plots there, sort of a time plot, injection pressure at the borehole, and then the injection pressure and the distance away from that borehole, showing a decline in the pressure exponentially away from the reservoir, away from the borehole in the reservoir. So those are really critical physical parameters. We mustn't let that injection pressure build up to the point where we cause problems with the integrity of the borehole or with the overlying seal. And you can sort of physically realize that the harder you push, the greater volume you can push in a limited amount of time. But you need to kind of dial back on the hardness of the push to avoid being in the risk zone where you cause problems. So that's the injectivity conundrum. Then there's the actual delivery. Can you deliver the CO2 to the injection site in a timely fashion? And then there's the long-term performance of the reservoir. Can you maintain the injection rates? Does it clog up? Do you encounter barriers that were unsuspected? And are the little pore spaces, the little nooks and crannies that I mentioned between the grains, actually affected by chemical reactions? CO2 is very reactive. So will it sort of self-clog and reduce the permeability? So those are the principal effects. There are also other effects that we won't dwell on. Induced seismicity can absolutely kill a project. It creates real trust issues with the general public if you have an earthquake. And here is an injection site off the coast of Spain, only 20 kilometers offshore. And the bottom diagram is a time series of all the earthquakes since September the 2nd, 2013, when the injection started. So you can see that's months, I think, that scale. Huge number of earthquakes of greater than magnitude 1, 20 to 30 earthquakes, and up to magnitude 4 and a bit. enough to be felt onshore, and that was a real problem for that operation. So sometimes you're going to get injection and it causes helpful fracturing that's not detectable as earthquakes. But sometimes you'll release more energy than you expected, and that threatens your social license to continue to store. And you'll be familiar, many of you, with the shale gas operations in Blackpool, called to a halt because of a couple of fairly minor earthquakes that created a lack of trust amongst the general public. So our risks here are really substantial. They're way bigger than the actual risk to life and limb. They're risk to general social license. The leakage risk is very difficult to quantify, and if we look at places where we're going to be injecting and we think about the storage of CO2, the things we have to predict here are really challenging. There's things that are a variety of scales that we can't see in the subsurface, and we have to postulate what those risks are and quantify those risks by geological knowledge and applying kind of a sort of geological common sense. If the CO2 leaks to surface, it could affect the ecosystem. Obviously, it's going to be bad from a public perception and trust point of view. And one of the big challenges is that the subsurface is inherently leaky. Fluids move through sedimentary basins. No seal is a perfect seal. So personally, I think this is one of our big risks, to actually persuade the public that some leakage is inevitable, but that it won't be anything like significant enough to cause environmental disasters, nor will it really radically damage the ecosystem to the point where the benefits of storing CO2 outweigh those localized risks and damage. Monitoring is expensive, but will be a regulatory requirement. So we want a light touch, efficient monitoring system that won't prejudice the economics of the technology and deploying the technology, but will reassure the public that things are not going wrong. So there's a whole bunch of things in that diagram. I won't dwell on them, but you can just get a flavour for a huge number of things that could be risks and that could also be sources of monitoring. So the leakage thing can be dealt with by monitoring gas at the surface, by using 4D seismic, by using microseismic, by using satellite data, by putting tracers into the CO2 and monitoring the migration of those tracers. So there's a load of different technologies that could be used, but we need to find the right blend of these that gives us the benefit at the right cost. The cost is going to be phenomenal. These are some of the numbers. You can have a glance through those. We need thousands of CCS projects to scale up to effective scale. We need to recognise that the cost of doing this will be phenomenal. I mean, it will be much greater than the current 30 billion investment in offshore oil and gas. It'll be many times larger than that in order to scale up. And how are we going to motivate our politicians to trigger the funding for that when we're just recovering from the largest financial shock in 2 centuries? So it's a big challenge, and it's your generation that will have to meet this challenge. I think my colleagues and I kind of all agree that we've got to do this. We can rise to this challenge. Technologically, we can do this. Research is going on a huge rate into this subject. There's going to be a need for a lot of skilled manpower in this area. It'll be one of the largest growth areas for employment for highly skilled professionals if we are to achieve net zero on the timescale that the saving of our ecosystem requires. So I hope you've got a flavour from that about CCS and the geological storage. Thanks very much.